Hey everybody, Mr. Brooks here again. So we are covering our last part of the information for test number 3. So this is 11.7 strategy for series. So this is referring back to every single series that we have talked about, and you'll notice I have some weird stuff popping up um, at the top here underneath our section title, and that's just because one, I was trying to play around with ways to memorize the names of tests and everything like that, and also we're referring back to these a little bit. So this is one, and the students from last semester and the semester before last also kind of agreed with these, and they actually came up with helped me come up with the next term that you see there. So you'll see gap and then the next word or phrase. So it's a reference to Marvel, but that's cool. We get to use that. But again, when you're going through series, think about what everything means. Okay. So first of all, what is a series? So I'm gonna be asking this question, and I want you to pause the video, think it out loud, and then play it and be like, okay, I got that right. I remembered what it was. So first of all, what is a series? A series is just a simple sequence, is a sequence of partial sums. Okay, and so what does it mean for a series to converge? A series converges when the sequence of partial sums, S of n, its limit exists and converges to a particular number. Okay, so again, the sequence of partial sums converges and its limit is equal to some value s. Okay, all right, what are some known series that we have out there? Well, we have the geometric series. So what are the conditions for the geometric series? All right, well, the geometric series form is AR to the n when n is equal to 0 as our beginning indice or index. Okay, and we know if r is the absolute value of r is between, or is the absolute value of r is less than 1, then the geometric series converges. If it's outside of that possibility, so if it's greater than or equal to 1, the absolute value of r is greater than or equal to 1, then the series diverges. All right, and if that particular series converges, then we know it converges to the value a over 1 minus r, which is really cool. All right. What's another series that we know? Specific series. Well, we know that there's the p series. The p series is of the form 1 over n to the p, where p has to be greater than 1 for the series to converge and less than or equal to 1 for the series to diverge. What's a known, very famous p series? Well, that's the harmonic series. It's 1 over n. It's our bread and butter example, if you will, for series. And we get to use that a lot when it comes to several tests that we have, especially the comparison test. All right. What's another known series that we have? Well, it's the alternating series. The nice thing with alternating series is we have a very specific test that goes with it. It's the alternating series test. So what are the conditions for the alternating series test? What has to happen in order for the series to converge? All right. So the series converges if, 1, the limit of b sub n is equal to 0, and 2, b sub n plus 1 is less than b sub n. So then that the terms of the series, absolute value of the terms has to be decreasing. So if we satisfy conditions 1 and 2, then we can say that the series converges. However, the series does not diverge if it fails those two. But the nice thing is we get to tie it into our very first test that we talked about, which is the test for divergence. The test for divergence states is if you take the limit of the formula of the series, a sub n, and you find out that it's not equal to 0 or does not exist, then you can say that the series diverges. However, the issue with the test for divergence is that it only talks about divergence. It does not talk about convergence. Okay, so if it does equal 0, then we still have to test on that. The good thing is we can typically then associate it with one of our other tests that we have out there. All right, the next test that we talked about is the integral test. So what are the conditions for the integral test, and then what are our conclusions about it? Okay, so the integral test requires that you find a function who is positive continuous, and decreasing on the interval from either 0 to infinity or 1 to infinity. The nice thing is we are allowed some bit of wiggle room with the decreasing. If it does increase for a little bit and then ultimately decreases, we can still use that function. Typically, we push then the interval to that value where it does start to decrease for the rest of the function. All right. So once we have that, the cool thing is that the integral test allows us to talk about specific convergence or divergence. So it's once we meet those conditions, we can talk about specifically, is it convergent or is it divergent? So that's the cool thing with it. So if you find out that the series is less than, or sorry, if you find out that the area underneath the curve of that particular function that you found, if it is convergent, then the series converges. However, if it diverges, then the series diverges. So that's the cool thing, is if you can satisfy those first conditions, then you know the series is either going to specifically converge or diverge. There's no gray area there. It's either specifically convergence or divergence. The next thing that we had was then talking about the comparison test. We had the direct comparison test and the limit comparison test. The direct comparison test was really nice because if you can do a term-by-term comparison to it, then, and typically we do this to a known series. We'll either compare it to a geometric series or a p-series if we're comparing it. Then we could just say, okay, well, we know it converges or diverges based upon that. So that's the cool thing. The bad part about it is that we have to be very specific. One, all the terms have to be positive, and we have to have a sub n is less than or equal to b sub n. All right. But the nice thing is once you satisfy either one's decreasing or increasing, or sorry, one is bigger and one is smaller, then we can do the conclusions of the direct comparison test, which state if b sub n, which is being the larger one, if it converges, then a sub n also has to converge. And two, if a sub n diverges, then b sub n also has to diverge. So that's our only two conclusions. If we find out that a sub n is convergent, but we're comparing it to an unknown series, we know nothing about the new series. Likewise, if we find out that b sub n diverges, that does not guarantee that a sub n diverges. So there are some issues with that test. All right. The nice thing is where the limit comparison test comes into play is we actually don't have to worry about this true term-by-term going on, but we do have to make sure, again, we're dealing with a positive series in that particular situation. So as long as a sub n and b sub n are positive, then we can apply the limit comparison test to them. Again, there's some caveats to all these as we go through, because again, if we had one particular test that worked for everything, I wouldn't go through the rest of these. All right, so with that, we take the limit of a sub n over b sub n, and the good thing is you do not have to worry about which one's the top one, which one's the bottom one. Either situation is perfectly fine, and because of what the next part of this is. So if we find out the limit of a sub n over b sub n, as n approaches infinity, is equal to some value c that is a positive finite number, then either one of the two cases happen, that either a sub n and b sub n both converge or they both diverge. This is why we use a comparison series to go with it, something that we know is convergent or divergent, then that way we force the other one to converge or diverge. All right, and then we got into, again, we've already talked about the alternating series test, and with that, there's the alternating series estimation theorem, that once you satisfy the conditions of the alternating series test, then you can say that the absolute value of the remainder is equal to the absolute value of the sum of the series minus the nth partial sum, S sub n, which is less than or equal to b sub n plus 1. Which is really cool because you can look at the b sub n plus 1 term and give us an error in that particular situation. So that's the really cool thing. So if we have a convergent series using and then it's alternating, we can then use that to say, okay, within a certain error, this is the approximate sum of the series. So that's a really cool thing about it. And lastly, we talked about the ratio and root test, which are really handy for those particular situations. So again, refer back to 11.6 for those guys. All right, so what are these letters up here? So here we have gap, which I'm going to refer to that, and it's actually intermingled in the next one as well. So you'll see the D, so the P, the I, and the G that pop up there. Those are the same letters for that. So gap represents G is equal to the geometric series. So this is a way just to remember how things are. A is alternating series. And P is P series. All right, the reason I referred to these guys, these are the ones that we know specifically about the requirements for these guys, or we have specific test that goes along with it. So alternating series has very specific tests that go with it. So that's where, again, this A, this G, and this P are coming from, is from gap, which is geometric alternating in P series. All right, the I, so let's go through and here how I read it is die pack rat Groot. So I like to say Groot just because I'm a Marvel fan for that part, so you get that piece in there. All right, but they specifically stand for the other tests that we have out there. So the D part is the test for divergence. Sometimes referred to as the divergence test, so that's why I plug both of those in there for that. So that's where the D is coming from. All right, the I is for the integral test. The C is coming for the comparison test. So we have the DCT and the LCT, so the direct comparison test and limit comparison test. The RAT obviously should be coming for the ratio test. And the root in Groot is coming for the root test. So that one is not as much as hidden, but there you go. So these are represent every single type of test and known series that we have out there that we have talked about from 11.2 to 11.6. So nothing new has been added to this. So let's talk about these real quick. So we know the conditions for the geometric series. Here, absolute value of R is less than 1 converges. And sum is A over 1 minus R. Now again, if n is equal to 1, we have to have it in the form of A to the n minus 1. And for P series, all right, for P series, we have P has to be greater than 1, and it converges. The integral test is really handy, but the big thing in here is it easily integrated? So let me put that. Can it be easily integrated? Because you might have an easier test to go with it. Like, is it a P series? Can you use the comparison test? That type of thing. All right. Ratio test is don't use, and I'm going to put that on here, on rational expressions. What I mean by that is do not use it with polynomials, or a polynomial divided by a polynomial. So ratio test has that pitfall there. Okay, so these are just some quick ones to go through on there. So next we go into, well, what are these questions here? So these questions are very 4 simple questions to go through and say, okay, I'm given any type of series, what the heck do I do? So this first question, does the nth term approach 0? Meaning, does the limit equal 0? If it does, then I go to questions 2, 3, and 4. If it doesn't, use the test for divergence. Because then you're done, because you know that this is going to diverge. All right, so if yes, see question 2. All right, so the next question, is the series in gap? What I mean by that, is it a geometric series? Is it an alternating series? Or is it a p-series? If it's one of those 3, then we can go to our very specific test there, either alternating test using properties of geometric series or using properties of a p-series. If no, see Q3. All right, so if it's not in gap, then can the integral test, so that's what the IT is, the root or the ratio test be applied? So first of all, is it a rational function? Then I'm not going to use the ratio test. Does it have a one thing in here also to emphasize? If it does have a factorial, use ratio. That's a good key indicator in there. Okay, so if it has a factorial, and I'm going to write that out a little bit cleaner. Use the ratio test on it because that's the best application for that. Okay. Does it have powers both in the numerator and denominator that when you take the nth root are going to either be simplified completely or have just a single term there? That would be a good example. So like e to the 2n over n to the n, when we take the nth root, we get e to the second power over n, which we saw in the previous lecture. So those are some good examples. Again, the integral test, a lot of people avoid it just because of its length, but we know it will converge or diverge, specifically if it fits its conditions. All right, and the last one is, if we can apply it, see question 4, is can we compare it to either the geometric series or the p-series? If so, use the direct comparison test or the limit comparison test. So those are their 4 questions. Very quick questions to go through. Am I looking at something that I can see its limit is not going to exist, or that it's, and be careful around alternating series just because of that alternating part. So don't immediately go for, I would suggest go straight to the alternating series test if you see it's alternating, period. All right, so very, very quick things to go through. So one note here, if the series does involve a rational or algebraic functions of n, should not be used in the ratio test. All right, so again, that's my big emphasis there. But again, if it does have a factorial, use the ratio test. It works out really nice and neat. All right, so that's really the big summation of this, is use gap, use Dipakt-Rat-Groot on this. Those, if you need to write it at the top of your test, you're more welcome to. Since this is open book, you can do whatever you want, pretty much. Just don't cheat. But this is the idea of these, is look through these real quick and say, okay, what can I use? So first of all, here are the 7 that we're going to talk about today. All right. So take a second and I want you to write beside it what type of test could you use automatically on it to determine if it's going to converge or diverge, or at least have a starting point on. So pause the video right now and then, well, here in just a second, and right beside it, say I'm going to use this test, this test, this test, this test. All right. And then I'm going to write the one that we're going to use for it. All right, so now that you've done that, let's look at this real quick. So I see n plus 1 over 3n plus 1. Automatically, I see ratio test is not going to be applied. Number 2, notice that they both have the same the power of n. So that means I'm looking at, in the end, when I take the limit, this is going to be talking about 1/3. So I'm going to use the test for divergence for this one. Okay. For this next one, I see pi 6 to the nth power. All right, since the base is staying the same, but its power is changing, that means it leads more to be a geometric series. All right, the next one, I have n e to the negative n squared, which can be rewritten as n over e to the n squared. So there's a couple ways I could do this. I could use the ratio test. That will work perfectly fine on this one. But here I'm going to use the integral test. And the reason I'm doing that is, one, forcing you guys to see the integral test one more time. All right, number 4. We have 1 over 3n plus 1. I'm probably going to use one of the comparison tests to it, more than likely the limit comparison test. All right, number 5. I see negative 1 to the n, automatically AST, alternating series test. Number 6. I see factorial, immediately going to go for ratio test. And the last one, I see everything raised to the power of n, root test. So see how quickly you can go through here with, and yes, I did already have these prescribed, but the nice thing is you can clearly go through these real quick and say, okay, these are the tests I'm going to try. If they don't work, there are other tests, okay? But try these tests out. If you get a conclusion out of it, you're good to go. You're done with the problem, okay? So there's nothing wrong with that. So question number 1, and I'm going to go ahead and work this one up here just because it takes a very short amount of time. Here, I'm going to take the limit as n approaches infinity of n plus 1 divided by 3n plus 1. This is going to give me the limit as n approaches infinity. And yeah, I'm going to write this all the way out. Excuse me. Sorry about that. So definitely have your volume turned down for that part. So if I divide all the way through by the largest power of n in the denominator, I'm going to get 1 plus 1 over n divided by 3 plus 1 over n, which leaves me with 1/3. So here, this is not equal to 0. So by the test for divergence, the series diverges. And you're done with the problem. That's all that are required. All right. Question number 2. I said let's try a geometric series. Well, pi 6 is less than 1 because pi is 3.14 and change. Okay. So therefore, this is a geometric series. Now, since n is equal to 1, it's not in that format yet, but we could write it as pi 6 times pi 6 to the n minus 1. Notice I only asked you to talk about convergence or divergence. So since we already established that r is less than 1, the geometric series converges. And that's it. All right, so the last tests 3, 4, 5, and 6, and 7, I'm going to write out below. But this is how quickly you can go through these. Again, I'm not trying to do this for speed. I'm just showing you that it is this simple to go through the process. All right. So question number 3. We said I was going to use the integral test. So f of x is going to equal x divided by, or we'll say x e to the negative x squared. Okay. So I'm going to look at the integral from 1 to infinity of x e to the negative x squared dx. All right. My work to the side for this particular problem is just looking at the very simple integral, because I'm going to have to get to it here in just a second. All right. I see x squared, I see x, so I'm going to use a u substitution. And we could make it negative if you wanted to. Doesn't matter in this particular case, but we can. So I'm going to let u equal x squared. So that means du is equal to 2x dx. So that means a 1/2 is going to come out. So I'm going to have 1/2 the integral of e to the, and we'll go all the way negative here. So negative 1/2 here. E to the u du. And so we get negative 1/2 e to the u, and we're done. And let's throw that back in there. All right, and so we can double check with this, and technically plus c, but we're not going to use that here in this. All right, so using improper integrals, I'm going to rewrite my limit as t approaches infinity. So we get the integral from 1 to t of x e to the negative x squared dx. We just found out what the antiderivative of this is, the most simple antiderivative. So we're going to get negative 1/2 e to the negative x squared. All right, evaluate it from 1 to t. So we're going to get the limit as t approaches infinity of negative 1/2 e to the negative t squared plus 1/2 e to the negative 1. Well, this is a constant value, so nothing bad there. E to the negative infinity as it goes, so that's going to go to 0. So in the end, we get 1 over 2 to the e, which means it converges. So by the integral test, the series converges. And that's it. All right. Number 4. So number 4, we said we were going to use the some type of comparison test, possibly the limit comparison test of this guy here. All right, so my a sub n is equal to 1 over 3 to n plus 1. I'm going to compare it. Well, the driving force here is b sub n, I'm going to say, is 1 over 3 to the n. So that series 1 over 3 to the n is the harmonic series multiplied by 1/3, which doesn't really matter in this case. So it's a harmonic. So it diverges. And since I'm putting this in my example, I'm already done with that piece. Now, since I'm using the limit comparison test, what I'm doing is I'm not having to worry about showing that one is bigger or smaller than the other. In this particular case, if we did do a term-by-term comparison, we know that a sub n is less than or equal to b sub n, which does not help us in this particular situation. So can't use direct comparison test. But if we look at the limit as n approaches infinity of 1 over 3 n plus 1 times the reciprocal of b sub n. All right, again, a sub n divided by b sub n. So here's my a sub n divided by b sub n. Sorry, did flip change. Sorry, keep change flip. Then I'm ready to go, because then I get 3n over 3n plus 1. In the end, I get the value of 1. Since this is a positive finite value, by the limit comparison test, the LCT, the series, here I'm going to be specific about it, diverges. And that's because when we get a positive finite value from the limit comparison test, either both converge or both diverge. And since we already used or comparing it to a divergent series, then the other series has to diverge. Just a nice little simple logic piece there. Number 5. All right, we have the series of 3 over 4n plus 1, and then I have this negative 1 to the n. All right. Immediately, I'm seeing alternating series test. So question number 1 is the limit as n approaches infinity of b sub n, which is 3 over 4n plus 1, is it equal to 0? The answer is yes. Number 2, b sub n plus 1, is it less than or equal to b sub n? Is it decreasing? All right, so that's 3 over 4n plus 5. Again, when you plug in n plus 1, I'm going to multiply that by 4, so I'm going to get 4n plus 4 is plus 1. So this is where I get 4n plus 5. Is this less than or equal to 3 over 4n plus 1? All right. If I cross multiply, I'm going to get 12n plus 3 is less than or equal to 12n plus 15. Subtract the 12 n's. Is 3 less than or equal to 15? The answer is yes. So by the alternating series test, the series converges. This means for this particular case, just to give you an example, if I asked you to determine the sum of the series to an error of less than or equal to 1/100th, then you could apply the alternating series estimation theorem for that. Okay, so that's another follow-up question that I could do with this particular problem. All right, number 6. Summation as n goes from 1 to infinity of n factorial divided by 10 to the n. I said we were going to use the ratio test, which is a perfect one for this because of the factorial. So here I'm going to get the limit as n approaches infinity of the absolute value of a sub n plus 1, so n plus 1, the quantity factorial, divided by 10 to the n plus 1, times the reciprocal of a sub n, which is 10 to the n over n factorial. All right. From before, I have an extra copy of 10 in the denominator. Here I have an n factorial inside of this n plus 1 factorial, leaving me the following. I will have n plus 1 divided by 10. And as n approaches infinity, this blows up to infinity. Since this is greater than 1 or goes to infinity, by the ratio test, the series diverges. And you're done with the problem. And our last one, number 7. And it goes from 1 to infinity of n plus 1 divided by 3. Did I use 3n or just want to make sure I have the right one down? 2n. 2n plus 1 to the n. I said use the root test. All right, so we're going to take the nth root of this. That's going to cancel out. We're left with n plus 1 divided by 2n plus 1. All right, so I'm going to take the limit of n plus 1 divided by 2n plus 1 as n approaches infinity, and I'm going to get 1/2. So this is less than 1, so by the root test, the series, and again, you've got to be careful on this, is absolutely convergent. Therefore, the series converges. Again, we did this really quickly. However, this is the approach. You ask yourself those 4 questions. is the nth term going to 0, meaning does the limit of the series go to 0? If the answer is yes, you move on. If it doesn't, you're done with it. You know it diverges by the test for divergence. Step 2, is it a known series? Okay, so question 1 and 2 kind of are at the same level in my opinion, because if you notice that it's alternating, if you notice that it's a p series or a geometric series, go ahead and go for question number 2. So that should be your identifier there. If not, then test for divergence is your next step. Okay, not saying that you immediately apply the test for divergence. I would try if you already have a sense that it's not, don't try it out. You're not going to get any extra points if you do. Again, I want to know what test you used and how you proved to me that it's either convergent or divergent. So once you go through those, can you easily use the integral test? Can you use the ratio or root test with it? Again, be careful with the ratio test. With polynomial functions or rational functions, those guys are going to be an issue. So I'd be careful on that end. But if you see a factorial, ratio test is your go-to on that part. And then lastly, can you compare it to either a geometric series or a p series? And that's it. So this will get you into everything that you need. So again, review chapters 11.1, or sorry, sections 11.1 to 11.7. That will be on your next test, which I'll be posting Friday. Also, I'm going to send out an email and everything on Canvas as well for that part. All right. Y'all have a wonderful day, and I will be doing a live Zoom meeting Thursday, hopefully, is what I'm planning on doing to answer any questions that you have regarding these particular lectures. Y'all have a wonderful day.